And welcome back as we continue our journey through our own solar system. We previously had talked a lot about the sun, but our sun, of course, has its own cycle, so let's go ahead and dive into that today. So the first thing when we are talking about the solar cycle is that we have to refer to this idea of sunspots. So before the invention of the telescope, the sun was thought to be an unchanging and perfect sphere. The first evidence, though, that the sun changes came from studies of sunspots, which are these large dark features seen on the surface of the sun that are caused by increased magnetic activity. Now, sunspots look darker because the spots are typically at a temperature of about 3800 Kelvin, whereas the bright regions that surround them are about 5800 Kelvin. Now, occasionally, these spots are large enough to be visible to the unaided eye, and we have records going back over 1,000 years from observers who noticed them when haze or mist reduced the sun's intensity. Now, when we start talking about sunspots, we of course have two images of sunspots here that we can look at in A and B. In image A, we can see in this image of sunspots some cooler and thus darker regions of the sun. This was taken in July of 2012. Now we can see the darker central region of each sunspot, which we refer to as the umbra, surrounded by a less dark region, or a penumbra. Now, the Daniel In image B here, we have, of course, a very, very detailed image of a sunspot, which was recorded back in January 2020. Now, and you can see how much more in-depth we get, and we can start seeing some of the granules and stuff here around the sunspot. Now, although sunspots appear dark when seen next to the hotter gases of the solar sphere, an average sunspot, when you cut it out of the solar system, left standing in the night sky, would still be as bright as the full moon. And again, this modeled appearance that we see here, both in image A and B, is very much a representation of granulation. Now, why do we have sunspots? Well, to have that, we need to first understand a little bit about the rotational period of our sun. By recording the apparent motions of the sunspots as the turning sun carried them across its disk, Galileo demonstrated that, well, the sun rotates on its axis with a rotation period of approximately 1 month. So our star turns in a west to east direction, very much like the orbital motions of the planets. The sun, however, is a gas and does not have to rotate rigidly the way a solid body like Earth does. Think about more like how Jupiter is, and we have like the different bands of gas across Jupiter, where those different bands are moving at different speeds. Now, modern observations show that the speed of rotation of the sun varies according to latitude. That is, it is different as you go north or south of the sun's equator in a behavior we know as differential rotation. So the rotation period of the sun is about 25 days at the equator, 28 days at latitude 40 degrees, and 36 days at latitude 80 degrees. Now, taking this back to our idea of sunspots, it allows us to think about the sunspot cycle because, believe it or not, sunspots are also on their own cycle as part of the solar health. So, although individual spots are short-lived, the number of total visible on the sun at any one time is likely to be very much greater at certain times. Sunspot maxima occur at an average interval of 11 years, but the intervals between successive maxima have ranged as short as 9 years to as long as 14. So the big thing is like 11, it's the average, but it can range from anywhere from 9 to 14. Now, during sunspot maxima, more than 100 spots can often be seen at once. Now, the key thing to remember is, though, even though there's like more than 100 spots, this means that this is only still less than 1/2 of 1% of the sun's surface actually being covered by these spots. Now, during sunspot minima, sometimes there's no spots visible at all. Like you might see none when you go. It'll just be a nice, looks like immaculate sphere. Now, this allows us to tie our conversation back to magnetism and how this relates to our solar cycle. Now, the solar magnetic field is measured using a property of atoms called the Zeeman effect. Measurements of the Zeeman effect in the spectra of the light from the sunspot regions show them to have very strong magnetic fields. Whenever sunspots are observed in pairs or in groups containing two principal spots, one of the spots usually has a magnetic polarity of a north-seeking magnetic pole, and the other has the opposite polarity. Moreover, during a given cycle, the leading spots of pairs in the northern hemisphere all tend to have the same polarity, whereas those in the southern hemisphere all tend to have the opposite polarity, which kind of makes sense. You think the sun is really, if you think about it, almost like a giant magnet. Now, during the next sunspot cycle, an interesting thing happens. The polarity of the leading spots is reversed in each hemisphere. So the north and south effectively flip. So, what does this actually look like when we start talking about the sun? Well, a good way to think about it is that these magnetic field lines wind up around our sun. So calculations do show that differential rotation and convection just below the solar surface can actually twist and distort the magnetic fields. This causes them to grow and then decay, regenerating with opposite polarity approximately every 11 years. These calculations also show that as the fields go stronger near solar maximum, they flow from the interior of the sun toward its surface in the form of loops. And if you think about it, that really kind of makes sense when we start thinking about the radiative layers and the convective layers that are within our sun. Now, when a large loop emerges from the solar surface, it creates regions of sunspot activity.